Hi, welcome to the Signal Path. In this episode, we're going to do a review of the Siglent SDM3055A, which is a 5.5-digit bench multimeter. Now, this unit costs 470 American dollars, or you could get it with a USB to GPIB converter for $630. There is no difference between those two versions, except for the fact that the USB to GPIB converter is bundled with one of the two that I mentioned. But if you're never going to use this, you can save your money and just buy the SDM3055, which is identical to the other one for $470, as I said. Now I want to do a fairly in-depth review of this. We're going to do a teardown, take a quick look at the specification, and do a bunch of experiments with it. I've been using it for some time, and I want to let you know what I think about it. Now, I highly recommend that you go ahead and download the datasheet and take a look at it for yourself. But just a quick few notes. The DC volt range on this multimeter starts at 200 millivolts and goes all the way up to 1000 volts, and we'll test those different ranges. And the current, the smallest, is 200 microamp all the way up to 10 amps. So 10 amp is a fairly large range for a multimeter of this caliber, which is pretty good. I'm happy with that. For resistance, the lowest resistance is at 200 ohms, which can make it a little bit difficult for very low resistance measurements, but it goes all the way up to 100 mega ohm. The diode test can give you 2 volts, and we'll take a look at that as well, which is pretty good. You can try out, of course, measure high voltage diodes like LEDs and so on and see if they turn on, but it doesn't report the voltage exactly. Anyhow, we'll get to that. And other specifications are fairly typical for a multimeter like this. In AC voltage, again, you start from 20 volt to 715 volt and 20 milliamp to 10 amp again. And it has a whole bunch of other functionalities, as well as frequency measurement, capacitance measurement. It has an impressive capacitance range all the way up to 10,000 microfarad, which is also pretty good. 10,000 microfarad is quite large to be able to measure. It supports a full range of different temperature measurement mode, the different type of sensors that you can connect to it, thermocouple sensors you can connect to it. It's just pretty self-explanatory and nicely documented. The manual is pretty good. English can be sometimes a little bit awkward, but other than that, it's fairly good to take a look. I'm sure you don't want to take a look at this paper right now. You want to see what's inside the unit. So let's go ahead and take it apart and then do some experiment with it. Alright, let's get to our teardown of not of this guy, but of this guy. Of course, this is a typical day here at the Signal Path, and I'm going to go ahead and take this guy apart so we can take a look at inside. I'm more interested in figuring out what kind of components are used, the build quality, and of course typical things that we expect from a bench multimeter of this caliber, for example. So it's going to be an interesting teardown. I won't spend too much time on it because I want to obviously use it in a couple of experiments to show you its performance. So let's get started. Here we go. I've taken the unit apart. As with a lot of these bench type units, you can really take them apart very easily by just removing 2 screws at the back, and the back panel comes off, and then the whole top cover slides off. And this one, interestingly enough, the security strip didn't leave any residue on the unit, so you could potentially stick this back on and no one would be able to tell that you've taken the unit apart. It's interesting that this basically didn't do its job. I wonder why that is. But anyhow, now if you take a look here, we can start from the main line coming from the outside of the unit, and here the fuse is of course built into this connector here, and there's a switch at the bottom which can switch between 110 volts and 200 volts. It can support up to 240 volts, which of course then switches between the transformer coils here to run it at a different voltage. And if you look here, they've paid obviously close attention to detail here. You can see that the earth ground is nicely soldered and a shrink tube going into a connector which directly connects to the chassis very nicely, and they've taken care to cover that as well. So a lot of attention to detail, making sure that this connection is always well made, which is a very important safety feature. Then they've taken the wires that come from the switch that selects the different voltages, and the input, they go into a separate board there, which has a MOF protection on it, and this separate board then distributes those signals onto the transformer. I like that, and they've obviously put quite a bit of effort making sure that these are nicely screwed to the chassis and nicely protected, so they obviously didn't just solder cables around. They wanted to make sure they have this really modular design, which this board then can be used, of course, for other projects. Another interesting thing to note is that obviously the transformer is made in China. It has Chinese writing on it, and it has triple output, so it has 3 secondary coils there, one of them putting out 32 volts and the 2 of them giving out 8 volts, and they're labeled of course with different colors and so on, and I cannot read the Chinese letters, and whoever can read them can tell us what it says. And another interesting thing is that even though this section is completely isolated, unlike the arbitrary waveform generator, the power supply isn't in here, and the only thing that this section of the chassis houses is basically just the interface board and the transformer itself. The secondary coil outputs of the transformer, the 8 volt, 8 volt, and the 32 volt, directly go onto the two boards that are inside the unit itself. As a result, the main power supply circuitry, the rectifier, the voltage regulator, and the circuitry that does the filtering are all on these boards. It's a little bit interesting. I guess they've done that for cost, and they've incorporated it here. We can see very clearly that the outputs, some of the secondary outputs go in here, and you can see clear the rectifying bridge is right here. Here's a voltage regulator. There's a couple of filtering capacitors. So here's a section for our first power supply. And then on the other board, which I'll talk about in a bit, you have another set of cables going in. Again, another bridge rectifier here, some filtering, and some DC-DC converter. There's some of it here, and there's some more DC-DC converters here, which are classic by the presence of those inductors, the buck boost converters, and so on. So these two boards actually are powered from two different, at least based on what I can see, from two different sections of the transformer. So one of the coils, this I believe is one of the 8 volts probably, goes into here and then gets rectified to 3.3 volts and so on, and 5 volt for the rest of the circuitry here. So by doing that, they have essentially transformer isolated the whole analog section from the digital section. This little ribbon cable that you see coming out here, which is taped to the connector at the bottom, is what controls the display. And you can see quite a bit of attention to detail because they've taped it down, so make sure it doesn't come out, because if it just comes out, obviously you have no front panel anymore. And then when it goes around, you can see again it's nicely covered by this black plastic container, which is clipped with these plastic clips onto the side of this chassis. And this further isolates that ribbon cable from the isolation transformer and just provides stability of this, holds it onto the side of this metal casing here, as well as making sure that it is yet further separated from the isolation from the transformer, isolated from the transformer there. It's, there is no clearance, it's obviously just touching it in this point, but it has a couple of layers of protection. Another thing I want to point out is that they haven't just obviously cut a hole in this, because if you just cut a hole in something like this, it will have sharp edges, and the cables that will rub against it are going to ultimately have perhaps cut and then be shorted out or connected to the chassis and cause a whole bunch of problems. So these edges are folded over, and they're quite nice. They're not sharp at all. I can put a lot of pressure on them. A nicely tied down cable here, making sure that it's all taken care of. And there is this cable that you see coming here with 4 lines on it. That's the front panel USB connector, and then it goes into this board. Now the main board here is obviously a 2-board construction. This is a very common technique. Other people do it. Agilent does it. Keithley does it. And this is a common way of separating the digital design, which can then be used for many different boards. This is something that Keithley has done on their source meters when I did a teardown of that one. So then this section, which has the application processor, the memory, the RAM, the flash, all that stuff, good stuff in there, interfaces like USB and Ethernet, can be used over and over again by changing the firmware to control a whole different instrument. So you don't have to keep redesigning this board, and you only work with that board. So here you can see there's a Texas Instrument application processor in there. This looks like some SRAM or some DRAM. Here's some flash memory most likely, and a bunch of other little things. The buzzer is there. Nothing really too exciting. This cable here connects the 2 BNCs at the back to this board as well, which I'm assuming then control the trigger, because the trigger is coming from this points at the back, which then of course connect to the digital section. Here's the Ethernet, here's the USB. Another interesting thing is that there's an SD card reader here, which I'm not 100% sure what it is for. Perhaps someone else has figured it out. Maybe for initially loading the main firmware onto the processor into the flash. Perhaps some other fancy things can be done. Even though it says an expansion option here, I have no idea how this expansion option would actually connect to this board. This connector that you see here, I suspect is for the GPIB, which is not populated in this unit, which will be another board, which then you will have a ribbon cable going from this to another expansion board, which then will be connected to the GPIB. I hope I'm not shaking this too much. I'm trying to hold as steady as possible. Another interesting thing is that, they've gone through the trouble of taping this down, but they haven't gone through the trouble of taping this down, which is surprising. I mean, why not put another 2 pieces of tape there? If you're going to tape this, then you recognize the potential of it coming off, then you should do the same thing here, especially because this is completely loose. There is no glue anywhere in here, but I don't think it's really necessary. These capacitors are fairly small. This heatsink is really solid onto The PCB I don't think is going to cause some issues. There's some opto-isolators here, which of course completely separate electrically, except for the ground, the two boards from each other, which is a common technique. The fan over here, which blows air into the unit, blows it over potentially to cool all the power supply units and runs over some of these components away from what I suspect is the reference voltage and the multi-stage data converter, which is underneath this piece, I believe. We'll get to that in a second. And you can see there's a lattice component here, which is controlling the glue logic for controlling all the digital circuitry here. Again, a very common technique to do that. And you can see the programming port of it here. Another interesting thing to note is that the main fuse, when this thing is set in current mode, is at the back of the unit here, and these are the two cables that carry the current onto the fuse and back. So, you know, there's going to be some drop across this and so on, which I'm sure is taken care of as part of the calibration of the unit. And there is no fuse access in the front. This is the only one at the back. There is yet another fuse in here, which is a ceramic fuse protected by this glass container over there. I'm not 100% sure what that is for, but that's perhaps a secondary fuse for some further protection and so on. And you can see that the input lines that come through some cables onto the main board. Now, obviously, everybody would prefer to have this design perhaps similar to what Keysight does, with a specifically made component here which goes directly onto the PCB. Basically, it's a plastic module with all the cables nicely next to each other. It's a very repeatable process. It's a very good construction. It's solid. It doesn't move around. These wires cannot move, for example, in that case, and that is a higher quality. But for something on this price range, this is the way they've gone with. And I believe a couple of other the Rigol equivalent one does the same thing, I believe. And you know, the disadvantage of something like this is, of course, that these wires can act like antennas. They can pick up noise, they can inject noise, they can do a whole bunch of different things, and there's always going to be some variability as a result of them moving around. But again, this is a 3.5-digit meter, and I wouldn't worry about so much about it, and this is to reduce cost, of course. I'm not even sure if the design that Keysight has is patented or not. Likely it is patented. But anyhow, moving on, you can see nice protection at the input here. Let me tilt this a little bit here so you can get a better look. There's protection, there's a bunch of spark gaps, some MOVs, and a whole bunch of relays here for other purposes. There's a rectifier here. This unit has quite a few relays which switch in and out for different functionality and different ranges of measurement. And these relays have some advantage and disadvantage. Obviously, a relay is rather slow, but it's very repeatable. It will last quite a long time. Not as much as a reed switch, for example, but it has very low on resistance and so on. It has its own advantages. And you know, but it is slow. So if you switch back and forth, you can see some ceramic resistor array here. There's another one here which supports a different footprint. Exposed PCB traces. Again, common technique for very sensitive analog voltages. And you can see a large series set of resistors there. The shunt resistors for the current measurement, I believe, are here, if I'm not mistaken. Again, this is the first time I'm looking at this, but there's some more protection circuitry there. Everything else looks pretty good and straightforward. I think the construction is very nice. If I were to look at this, again, it has no mistakes and there's no budges in it. Everything is nicely tied down. I would have liked to see a better way of doing this, but hey, this is how all of these things are. There's nothing you can do about it. But I'm very happy with seeing all the important techniques that you would expect to find in a multimeter is deployed here. And this is the market now. We have Chinese manufacturers designing things that, when you look at, looks just like anything else that a high-end manufacturer would produce, which is great because it is a competition for everybody to up their game, essentially. There's this high resistor values soldered onto this spark plug here, is a spark gap here, which is another interesting thing. This is the only thing that seems like it's done by hand later on, and these cables are obviously soldered by hand. So it looks good. I don't want to waste too much time on this, but again, if you want to see any more details of it, if you want to know what exactly these components are, I can always post them onto the forum afterwards. Other than that, I am happy with the construction. I don't see anything immediately wrong. Nice clean layout, nice two-board construction, obviously upgradable with firmware, and I am running the latest firmware. I know that the earlier firmwares had some problem, and I spoke with the Siglent representatives who are very responsive in trying to get these things solved. So I'm running the R12 version, the latest version of the firmware here, which we're going to use for our testing. One other comment that I want to make is that the transformer is very nicely tied down, so it has much larger screws in here. So the only thing that would normally be in danger of being ripped off the board or ripped off the chassis if this thing falls is this is the heaviest unit, but I think it's really nicely tied down. I honestly wouldn't worry about it. The chassis is in a high quality. I don't see any rust or anything like that with it. You can see they've taken great care making sure that everything lines up. Pretty happy with it. So I think got a pretty good look at it. So the next important thing is obviously turn it on, do some experiments with it, and do a couple of comparison with some of the other units that I have in the lab. But so far, pretty good. So here we have the Siglent SDM3055A front panel, and you can see that most of the area is of course taken by the LCD screen. And by the way, it's sitting on top of the Siglent SDG5162, which I reviewed before. Now I'm going to go ahead and turn it on so you can see the boot up time. This is on standby mode. It doesn't have a hard power switch, it has a soft power switch, and this LED is really bright. Legend has it that they use the SDM3055A to warn off ships at various coasts around the world. So let's go ahead and turn it on, and you can see it boot up slowly. Now I like the way the front panel configuration is. It's really easy to use. The white buttons are the functions, and the gray buttons plus the shift perform additional tasks, as well as of course you have the range button, directional switches, and a whole bunch of soft panel switches at the bottom. A front panel USB to of course load settings and take settings off, and put the firmware on and so on. And then we have the 5 terminals here, 2 of which are used for voltage, current, diode and capacitor measurements, and 1 is dedicated for a 10 amp current range. There's only 1 input for the current range, and there's of course the high sense and low sense ports. Now for an entry-level product like this, I really like the fact that it has a nice big LCD screen. It really does make a big difference when you have a big LCD real estate to use for functions. You can have larger numbers, and also as you develop the firmware, you have the ability of adding functions and graphing capabilities and other things which you may not have right off the beginning. So it's nice to see that. Now the LCD screen is good, it has good viewing angle, it has a matte finish, so it's not very reflective, and I'm generally happy with it. It's bright enough, it can even be made brighter than this. And generally a good LCD screen definitely for this price. Now, one of the very first things I noticed during the time where I've been using this instrument is that it really is very straightforward to design. It's very simple, and it's good. It's a good meter for people who are just beginning to learn electronics, or people who do not have an extensive knowledge about all the advanced functions. And of course, at the same time, the fact that it's very simple means that its functions are somewhat limited. So the way I have configured mine is that it boots up in the default mode. So this is what you're going to see, and you have the speed selection here, which I assume is just the number of power line cycles that it adjusts, and as a result of that, the resolution will also change. So this is right now in slow, and it also has an option of middle, which I'm assuming means medium, and then there is a fast option. So if I put it, you can see the update rate right now, and there's the auto trigger here, which will blink every time a trigger event happens. And if I put it into the middle, like so, you can see that you will lose a digit. And then if I put it into fast, and this is the fast mode, it still has a digit, but you can see that it updates much faster. Now, I would say that probably my biggest complaint about this meter, the thing that is probably a frustrating aspect of it, is that it is very slow. And that's partially because I've gotten used to meters that are much faster, and that could be why to me it appears to be very slow. So you're gonna have to look at it and tell me if this is something that's a little bit slow for you. We're going to do some tests and measure some of these aspects, but generally that's really is my most immediate concern, is the fact that the update rate is rather slow. Of course, other things such as filtering is available also to filter the results as they become available, and you can also do a relative measurement. So as soon as you press that, now it's going to do a relative measurement. You can turn it off and it will go away. So like I said, really very simple. You have DC volts, you have AC volts, and then you also have, of course, measuring resistance, measuring capacitors, a continuity test, and there is also a temperature measurement, and we will go do a couple of these things to try them out. And with the second function, you can then select the other things, for example, like current, which is nice because now you can only select the current by pressing shift first. So for example, like this, it puts me into a current measurement, and now it's on a 200 microamp range. Of course, there's nothing connected. and we can go ahead and figure some of these things out. So, I think as a starting point, probably one of the quickest thing we can do is just measure some standard voltages from my voltage reference here, so we can figure out, how the accuracy is and if it's giving us reasonable values. Let's go do some basic standard measurements, and for that I'm going to use my voltage reference box here. This is the DMM Check Plus, which I've shown in some of my other videos, and this one has a DC voltage reference, it has resistor references, it has a DC current as well as some AC signals on it. It's very nice for checking the performance of your multimeter. Now this is a calibrated unit. I've measured it also with a meter that exceeds the specification of the Siglent one, so I know the values, what they should be. So we can go ahead and try them on, starting from just measuring some basic DC voltage. Now one of the little thing I wanted to mention is that once this instrument is turned on, you can't turn it off by pressing this button rapidly. You'll have to hold the button in before it turns off. It's a nice little feature, so that if you accidentally press it, the meter won't turn off. I like that. The other thing is that in the camera, you might be seeing it, and this color might look a little bit blue to you. It's because of the extreme angle of the camera. I'm looking at it from above. If you look from above, there is a little bit of a discoloration in the screen, but from my angle, it's nice. The background is black, and that's probably just an artifact from the camera you're looking at. So let's go ahead and plug this in and measure it. I'm going to try and measure 5 volts. Let me find the output here. There it is. Now, once I plug in the plus sign, you can then correlate that with how fast it takes for the instrument to go from the 200 millivolt range to a 20 volt range that it needs to jump to. Here we go. There, you can see it does take a bit of time, and this is what I was pointing at. If you're okay with that, then it's not a problem. Again, like I said, depends on what you're used to, but other than that, no complaint about any other aspects. So you can see this jump to 20 volt, and it says 4.9999 or 9998, which is extremely accurate. That's exactly what it should be. In fact, the reference is just a little bit below 5 volts based on my last measurement. You can see that it is essentially correct, and it's very, very accurate. And of course, it doesn't matter if I change the speed too fast. It's just going to lose a digit, but then it rounds it up to a 5 volt value. And one thing I noticed is that when I put it onto the slow mode, you can see it takes a little bit of time before the measurement result that it did under fast condition disappears from the screen. So if I go under fast condition, you can see the 5 volt. Now it says there's a 1 at the very end. And I go to the slow, you can see it carries that with it, and then it updates. In reality, it should display nothing before it displays the other value. Or maybe I'm just a little bit nitpicking here, but it's important because you can cause confusion when you're doing a quick measurement. So there's our 5 volt measurement. Let's measure current. And for current, we're gonna disconnect this guy, connect it to our current port. I'm gonna take this guy out, put it in here, and we're going to just jump to DC current. And again, I'm going to plug this in. It's in the 200 microamp range, and it has to jump to a higher range. There we go. And it's settled already. And 0.99945. Again, it's quite accurate. It's supposed to be about 1 milliamp, and that's exactly what it is. Again, everything is just under the value that is specified based on my last measurement, and that's how this has drifted over time. And again, similar thing, you can change, how fast the sampling happens and so on. But no problem. Again, I'm going to disconnect. You can see that it jumps back and again to go back to 0. So looks good. I can also measure frequency. This thing has a frequency generator on it. So I'm going to go ahead, connect this back, turn this to AC mode, and switch this to frequency. There we go. We're going to plug this in here, and then we're going to wait. It's going to settle down. There it is. 1 kilohertz, and that's also what it should be. Like I said, it takes a little bit of time for it to figure out what it's doing. I'm going to disconnect again, and it jumps back. So it also has to change, of course, the vertical scaling or the voltage scaling before it can measure the frequency. So you have an idea of what the voltage is, because it does tell you. You can see it says 200 millivolt. Once I plug this in here, it then jumps to 200 and then jumps back down to 20 before it can tell you what the frequency is. But you can see it's dead on exactly what it should be. And for the sake of completeness, let's do some resistance measurement here. I'm going to short these two cables out. You can see that it takes a bit of time for it to jump back. Now, as is the residual measurement, I'm just going to turn the relative on so that we are back to 0. So let's go ahead and plug this into 100 ohm resistor, like so. and it's going to auto range 200, and there it is. 99.984 is pretty good. That's what it's supposed to be. And I can also go to the highest one, not just so that we don't have to measure every single resistor along the way. And this is a 100 kilo ohm resistor, and it should be 100 kilo ohm. So it looks good. Again, I like the display, nice big numbers, and we'll go through a couple of the features of there, and you can see that it clearly says at the very top here what you're measuring. So if I switch to DC volts, it will immediately tell you that. And this is a good thing to do because these buttons don't line up, unlike the Rigel unit that I have here on the left, where depending on the the measurements that you're doing, the buttons light up. This has no LEDs on the front panel except this eye searing one. Other than that, you have to look at the LCD, which is fine because the Rigel has a very small, just a monochrome LCD, not a full color one like this. So let's try some continuity test here. Before we do, I want to show you the probes that come directly with the instrument. They're quite nice. I like the feel that the wire are soft, and that makes a really big difference in how you handle the cables. You do want a nice soft cable so that it doesn't really get in your way. Now these things come with plugs at the end. This is the end that plugs into the instrument. They're shielded and guarded, of course, and you have protective tips for the main probes. Now the tips are really sharp. I like them, quite good quality. They're easily sharp enough to penetrate layers of flux or oxidized traces on a PCB. Very nice. I'm quite happy with them. I've been using them for some time. So let's go ahead and plug that over here. And over here now we are in continuity mode. And in continuity mode, one of the things you can do is you can actually tell the instrument what you want your threshold for the continuity to be. So right now it's set to 50 ohms by default, and I can change it to whatever I want, to 20 or 30 ohms. It doesn't matter. And you can continuously adjust that, and it says open, of course, if everything is open, and you can turn the beeper on and off. So now the beeper is on. Let's go ahead and listen to it. You can see that because the instrument is a little bit slow, it can actually miss connections. See, I have to spend more time. That's the only unfortunate thing. In continuity, speed really does matter because you do want a quick reaction time and you can miss it. But the best way to really appreciate whether it's suitable or not is to try it on a PCB. So let's try that. So here on this PCB, I want to find a connection between the connector here at the edge and find out where on this board it goes. So sometimes the board is multi-layered and you can't tell where all the connections are. So in this case, I want to see how easy it is to find that connection just using the continuity test on the Siglent meter. Now what I've made is this little brush, just a little bunch of wires together connected to this alligator clip, and these brushes are quite useful to make if you're looking for signals because it kind of makes contact with multiple pins at the same time, allowing you to nail down or narrow down your search. You can even make it more bushy kind of and have more area that you're searching. So let's go ahead and try. You can see obviously if I connect it, we'll pick it up. So let's go ahead and try here and do a little bit of a search here. So you can see I can drag it across these components. Oh, you hear that? There it is. So if I go fast, you can see it kind of misses it. But then if I go closer, it's this pin right here. So really when you're searching around a PCB like this, it may not be such a big problem to look for something. All it means that you're going to have to be a little bit more patient. I also want to measure the voltage it puts out in this mode just to see how high it is, because sometimes the voltage coming out of the instrument can be high enough that if you're searching over here something like over a PCB like this and you have a MOSFET transistors, for example, that could be rated only up to 1.8 volts or even 1.0 volts, then you could potentially damage the oxide of those devices. So let's do a quick measurement and see what voltage is putting out. So in this setup, I can measure the output voltage that is used by the Siglent multimeter in continuity mode directly on my Rigel multimeter. And so this is a voltage that the Siglent is going to use to detect continuity. So naturally, the higher the voltage, easier it's going to be for it to detect a short because it can detect smaller amounts of current. Now, this is important again, as I was saying, because you don't want to damage a component that has a low breakdown voltage. So it's always good to test this on any meter, not just a Siglent one, just to see what kind of voltage we're dealing with. I've put this Rigel multimeter into 10 giga ohm input impedance, which would then allow us to have essentially an open circuit on this side. And we're going to go ahead and plug this in. And we are seeing 6.9 volts, which is kind of rather high. make sure that you can see this. There it is, 6.95 volts, and that is the voltage put out by the instrument when there is nothing connected. So if you have a MOSFET, for example, that has a breakdown of 1 volt, and you put 6.9 volt across the gate and the source, or the gate to the drain, you run the potential of damaging it. And at the same time, of course, this thing is going to be able to deliver about a milliamp of current, and we can measure that by switching this over. And you can see that it's reporting continuity. Let me turn the beeper off, and we're going to go under current, milliamp current. There it is, 1 milliamp, and under 1 milliamp of current. So you do have quite about a milliamp of current that this instrument can provide to you. Now this is normal, but we can also do the reverse, and just to find out what for example, the Rigol does in continuity mode. But before I do that, I also wanted to show you very quickly on another potential, and just a reverse situation where I can put this guy under voltage and I can put this guy under continuity mode. Now we have the exact reverse. You can see that the Rigol puts out 5.8 volts, which is about a volt or so less than what the Siglent does, and that's normal. That's fairly typical depending on what instrument you're using. So here I'm going to use the Fluke. If I plug the Fluke in, I'm going to focus here on this voltage, and the Fluke is also in continuity mode. I'm going to plug that in like so, and you can see that the Fluke is going to use 5.3 volts, which is a little bit lower than both of them. Something to consider. It may not necessarily be a problem, but it could cause an issue if you're measuring very sensitive electronics. So another thing I want to measure is I want to measure the reaction of the Siglent multimeter to very high voltage inputs. I want to measure up to 1000 volts, which is what it is rated for. Now there's two things I've done. One thing is that I have connected, I have kind of wrapped around the two cables at the input of the instrument together, and I've done this to basically make it as easy as possible for the cables to fail if they are going to fail at high voltages. By bringing the two copper centers as close together as possible will allow the dielectric breakdown to happen at earlier voltages. So essentially I want to stress test the cables, and we will do that after the first test. The second thing I've done is I've connected it directly to my newly repaired model PS350 high voltage source from Stanford Research, and this can go up to 1000 volts, up to 5000 volts, and right now I've set it to 1000 volts, which is the limit, recorded limit for the Siglent. Now the Siglent is supposed to have input protection for above 1000 volts, so you would expect the input protection to kick in if I were to put more larger than that. So let's go ahead and see how it reacts to 1000 volts. Here we go. I'm going to go ahead and enable that. There it is. And you can see that it's going to take a little bit of time. It's kind of clicking back and forth, trying to find the voltage, and there it is. There you go. There you go. It just jumped to at 1000 volts. So there's a little bit of a delay, as I mentioned before. And again, the input impedance is 10 mega ohms. So you would expect the Stanford Research source to tell us an input current of 0.1 milliamp, which of course makes sense because there is 1000 volts over 10 mega ohm. And at the same time, we can see that it's giving us exactly 1000 volts. So let's go ahead and exceed the rated input and see what happens. Let's go to 1100. Enter, and you can see 1100, no problem. It's supposed to have input protection as 1000 volts, but it's not kicking in. So let's go ahead to 1200. There we go, 1200. It has no problem measuring 200 volts above what it is rated for. Now, normally I'd be happy with that. I'm just a little concerned because the input protection should kick in and protect the circuit, but so far it has no problem displaying that. So we can go a little bit higher. We can go 1250, and there you go. Now it says overload, and if I go to my instrument here, you can see that it is drawing 125 microamp, and it's supplying it at 1250 volts exactly, so that everything is still working. The input impedance is still maintained at 10 mega ohm. It's not, doesn't have any problem measuring that. Now I can go back down to 100 volts, for example, just so we can jump all the way down, and we can see that, there you go, it jumps to 100 volts without any issues. And I can go back to 1000 volts just so we can see that it is indeed still working correctly without any problem. So I didn't really kick in any input protection in the sense of disconnecting the input or shorting it out or anything like that. It behaved quite well, even well above its input rating. Now the other thing I can do, I'm going to go ahead first of all disable the output here. Now next thing I'm going to do, I'm going to disconnect these. I'm going to just lay them on the table like so. There we go. So under this condition, the cable is completely exposed. There's the two ends are open, they're wrapped together, and I'm going to set the input to 5000 volts, and just to see if the cable will break down. Here we go, we're going to set this to 5000 volts, enter. We're going to go ahead and enable that. Oh, there we go. And here's 5000 volts. There's 5000 volts on that cable. The cable is wrapped together. I see no dielectric breakdown. It behaves quite well. It's maintaining 5000 volt across it. The cable is quite nice and safe. So I wouldn't be worried about it. This is 5 times the voltage rated. So the electric field between the two halves of the cable are quite high, but it maintains it without any problem. So these are high quality cables. I wouldn't worry about them even if you accidentally connect them to a very high voltages. Of course, you should never do that because they're not rated for those voltages, but at least the dielectric isn't breaking down. So next I want to show you some of the plotting capability of the instrument, which is probably my favorite part of the way this unit works, because it's really easy to use and it can be quite useful for day-to-day measurements. Now what I've done here is I've connected the Siglent multimeter into a resistor decade box using 4-wire measurements. So these are our sense wire and these are our main measurement points here. And this is not the most accurate resistor box, but this will demonstrate what I want to do, and you can see also that I've put it into the unit, into the main measurement ports as well as the sense ports, and it is in 4-wire measurement mode. So if I go ahead and dial in, for example, let's say 10 ohms, you can see that it should give me 10 ohms, and it does, and it's very, very accurate. And if I go back to 0 here, you can see that the instrument tracks back exactly. This 19 milliohm that you see is going to be the difference between how these connections are interacting with each other. So that's normal. That's perfectly close to 0 as far as I'm concerned. 19 milliohms is very, very little. So I can also go in and step in 1 kilo ohm, for example, and you can see that it will switch ranges and it will jump to 1 kilo ohm, which is pretty good. When I said that this resistor box is not very accurate, I was talking about its lowest range. So if I go again and use the 0.1 ohm steps, if I go up by 0.1 ohm, you can see that it does kind of go by 0.1 ohm. It's not exact, but it's fairly close because the contact resistance need to be cleaned. And there's another 0.1, here's another 0.1, and it's not so bad. Anyhow, so what I want to show you is the different plotting capabilities. So let me focus into the instrument screen because we don't need to really see the resistor box itself. Here we go. So if I press shift and go under display, you can see that it will give me a bunch of options, and this is the first option, is just number display. Just this is the default way, just showing the numbers. Now if I press that, I have a couple of other options, bars and trends and histogram. Let's start with the bar. Now a lot of people like this bar. I also like it myself, and the reason this is a useful feature is because it tells you where you are in the selected range, and that's important because the range gives you some feedback information about the accuracy of the instrument for within the range. For example, the accuracy of measuring low resistance is going to be better when you're in the 200 ohm range than if you switch to the higher range. And this bar will basically go over the range and tell you how much of your range you've filled up. So here we have 200, I can dial in 100, and it should go right to the middle of the range, and in fact it does. And if I go ahead and click another one, 200, you can see that we are still in the 200 ohm range. Now instruments typically support going over the range by a little bit, so I should be able to go up by a couple of tens of ohms, and it still should remain in 200 ohm range. Here we go, that's another 10, so we're sitting at 210 roughly right now. I'm at 220, you can see that we're exceeding the range right now. There we go, 230, and now it's plotting beyond the axis there. And then one more, and then 240, pretty good, still in the 200 ohm range, and one more and it should eventually switch. There it is, and it switched now to the 2 kilo ohm range at exactly 250 ohm. It's very, very accurate again, and you can see the range is now 2 kilo ohm, and of course if I go ahead and kick in 1 kilo ohm, it will continue to build up the range. And there's another 2 kilo ohm, 1 kilo ohm, now it's just above the range, and if I go one more, it's going to jump to the next range. Now it's the 20 kilo ohm range, and we have 3.25 kilo ohm. So this is very, very useful. The horizontal scale can be adjusted. I like the default, but you can also set it manually. I prefer it, the way it deals with it. It does a fairly good job on its own. So while we're here, I also want to show you the hold capability of the instrument. And as with any advanced multimeter, this is going to have the capability to do hold measurements, so automatically detect when a new measurement is being done, so that it will enter it into a list for you when you're jumping between components. This can be extremely useful if you're trying to collect some data. So let's go ahead, and I've already enabled it. I'm already under the hold menu here. You can see that I have the hold here, and the instrument says that the probe hold is on, and if I turn it off just like that, it will just go back to the histogram measurement we had. So I'm going to go and enable it again, and the beeper is on. Now it is measuring continuously in the background, but it will only detect a new measurement once it feels like a new measurement has changed sufficiently that it would be considered a new unit to be recorded. So you can see the live value is shown over there at the very top. I like that. Let's go and give it 10 ohms. There we go. You can see that it detected that as a new measurement, and it added it to our list. And I can go give it another, let's say, go back to 0, and it measures that again. Now we are back to 0, and I can give it 1 ohm, and it misses that. See, so it doesn't consider a 1 ohm addition as a new measurement. So I can dial in another 1 ohm, and nothing. The change is simply, oh, there you go, it just picked it up. So once it crossed the 5 ohm difference from the original measurement, it counted it as a new measurement. I can go back to 0, and it counts it again. So it depends on how much measurement variation there is, and I can make a really large measurement. Here's 100 kilo ohm difference. There it is, and it added it over there. Again, my only complaint, just the speed. It's a little bit slow, and it takes its time. Right now it's on slow measurement mode. So if I go ahead here and change the speed to fast, it is going to do the measurement, of course, much faster. And I can go under hold again and clear the list. We can try again. 0. There you go. You can see it's now much quicker. There, see? It does it as soon as I change. There we go. Very nice. So you're going to have to make, if you're a little bit impatient, you're going to have to make a bit of a compromise between speed and accuracy. But other than that, in this mode, it's pretty quick. Very nice. There we go. There's 1.6K. I can add another 100K. And no problem. And it has all the information here. I like that it tells you what the current range is. It tells you the live value. The graphic user display is very nice. Very simple, very easy to use. I like it. Now, as far as I can tell, I don't think there is any way to combine this hold with any other type of measurement. So if I turn the hold off, and it takes me back to this view of the bar graph, and if I go under display, and if I change it from bar graph to, let's say, histogram, like so, and I will talk about the histogram in just a second. Let me clear the readings here. You can see that if I go back to hold, it just takes me back to this menu. So it doesn't combine the functionality between the various modes. In hold mode, it's strictly on this kind of spreadsheet type of style of display, which is fine. It's just something to consider. Now, the other pretty useful type of display that this thing supports is the trend chart. Now, the trend chart is, as the name suggests, let me clear this, is basically a graphic display that plots the trend of your measurement as a function of time. Now, this is going to update depending on the speed of the measurement. So in this case, since we're doing fast, for example, it's going to update fairly quickly. And if I go back under display, you can see that you can have an auto scaling. You can do your vertical scale to be manual or to be automatic. I like it to leave it on automatic. And then it also has one other thing that I like, is that it shows you all the measurements or your recent measurements. In a recent measurements, it's basically a scrolling plot, and as the new data come in, they basically have a window of time which you can set, and then this will just continuously go out through the window as things new measurements are done. So right now we are on 1 kilo ohm, so you can see there's a bunch of basically noise measurement. The scale is really small here. So let's go ahead and go from 1 kilo ohm to 2 kilo ohm, and you can see that all that noise collapses because the scale changed, and I can go 3, 4, 5, and so on, and I can go backwards, and you can see that it shows you, a nice measurement graph. It's very helpful if you want to look at it, obviously a trend on something, but it works really well. It's very easy to use. They've simplified the GUI, making it quite nice. And if I go, of course, under all, then it will just continue compressing the plot, and you can see that the elapsed time will now increase because the x-axis is being continuously compressed. And I can add another 100 kilo ohm, and of course, as soon as I do that, this tiny measurement that I have is now insignificant compared to the new values being added. Now I'm all the way to 0.3 megs. and go up and down again, just like that, and come back down all the way to 0, just like that. So it works fairly well, and I have no problem with it. And one last thing to show you is, of course, the histogram, and I can go and change that to histogram. We can go ahead and clear that setting. So right now I'm set to 2 kilo ohm, so it's continuously making measurements, and the binning is set to auto, which is usually what you want to have. Also, you can have the cumulative measurement on, and then you will see the plot on top of that. So right now we are at 2 kilo ohm, and if I go ahead and add another kilo ohm to it, you can see that it now has created another bin over here, and it's occupying that bin, and it's continuously building more measurements here, so you can see the measurement has changed. If I create another one, now a new bin has been created, and then I can continue doing this. This is very useful if you want to, for example, if you're continuously checking something and you want to see if the value deviates from the center. And let me show you what I mean by that. So here I'm measuring a 5.5 kilo ohm resistor on the resistor box, and you can see that most of the bins obviously land very close to that value. And if I go ahead and clear the readings, you can see they will continue to build the values. Now if I go and change it by 100 ohms, you can see that a new bin is created where the values are being populated, and I can go back and go 100 ohm below, and then you can see more bins being created. So you can clearly see me going back and forth between these, and creates bins, and I can go by 10 ohm steps, and now a new bin is created here. I can continue creating more bins, and this is obviously a statistical distribution of my measurement, and this will be very useful if you want to build a probability density function for all your measurements. Now if I go ahead and clear this value and I go under hold, it takes me back to the hold menu, and I can go and change my hold values. Of course, you can take individual measurements as I showed you. It would have been nice to be able to apply the hold directly on the histogram, but the histogram is being built in the background. It's continuously building it as I'm doing these measurements. So as you can see now, if I go back under and turn this off, you can see that it's been building in the background. Now it's not exactly what I was looking for, because you can see the probability density function live as you do individual measurements, which is really one of the main things you'd want to do, because if you're building this histogram by doing multiple measurements, every time you lift a probe, it's going to create a new bin with a value of 0 unless you go on to single, in which case you press single, and every time you do a single, you can see the acquisition is now stopped. So you can do individual measurements. But if I go ahead and clear this reading, and I go to hold mode here and take a couple of measurements like so, just a whole bunch of different measurements, and I go back to turn this off, you can see that it's built a lot more value than what I've actually measured. So anyhow, that's one little thing that I would have preferred if it was doing a little bit differently, because as soon as you go back to this menu, of course you lose your histogram because it's making new measurements. That's one thing that obviously can be easily added in software, and I hope that that's something that they would consider. Now the instrument does have a fairly good reasonable set of acquire functions, so you can acquire with a certain number of delay as opposed to automatic. You can also tell it how many samples per trigger you want to set. So if you use the trigger option from the back, you can actually set how many samples you want to collect per trigger event, or if you just want to trigger individually, you can tell it how many measurements to take per trigger event. This can be pretty useful if you're collecting large amounts of data. Now under the math menu, you do get a couple of options which can be pretty useful. I like the statistics menu, of course, because it gives you a quick view on the statistics of the measurements you've collected so far, and of course you can clear it and so on. That can be shown on top of any of the display modes. Right now I'm on a basic measurement display mode, so I've been measuring a 14.4 kilo ohm resistor, so you can see, for example, the standard deviation is really small, the span is quite small, and as soon as I add a kilo ohm to it, now you can see my span has changed, and the standard deviation is going to grow as the total amount of samples is growing. You can see there's 4.8 kilo samples, and is rapidly rising. So it is making quick measurements in the background, and it's displaying and updating the statistics menu, which can be quite nice. And if I go ahead and clear it, it will start from scratch. Under the limits menu, we can set a limit of measurement, and that can be done in any measurement setting. Here I'm doing it in ohms, of course. Now I can set what the low value and the high value is, or the center and the span. So the low value I've set to 14 kilo ohm here, and the high value I've set to 16 kilo ohm. So any value between those two will be considered a pass. So you can see they will here tell me the status is right now in pass. The low limit and high limit are all displayed, and it has no low failures and no high failures. So let's go and add a couple of values and see what happens. So there you go, we can go all the way to, it continues to pass, of course, 15.9, and there you go, 16.03 is failing and is measuring a whole bunch of failure modes. Now something like this is obviously useful with a single acquire menu, which would be the single trigger menu. This way, every time you do a single measurement, you can get whether your measurement is being failing or passing. Now, having said that, I would have liked again to see this with the hold menu incorporated into a single thing. So let's go back here, for example, let's take a single menu, let's clear everything, clear all the conditions, and go under continuous triggering again, and go under math, and under our limits menu again, so you can see that everything is passing. And if I go to a hold menu like this, and I clear the statistics, let's see if it will register a failed measurement. There we go. So this should be a failed measurement. Now if I turn the hold off, you can see that it starts from scratch. So no, it's not taking it into account in the background. The hold functionality isn't very well incorporated with the other capabilities. I wish it was, but I like the fact that, of course, it colors the background, gives you a quick indication that something's gone wrong. So here I have a very simple circuit. I have a lithium polymer battery that's connected directly to a power resistor, and the value of the resistor is 10 ohms, and the battery is being discharged through the resistor, and of course this resistor is getting hot. So if this is 10 ohm and this battery is about 4 volts or so, we're having 400 milliamps of current. Now of course I can measure the voltage of the battery directly with a multimeter, and I can also measure the current that the battery is supplying to the resistor. Now what I've done here is I have actually closed the circuit through the multimeter itself. So the voltage ports of the multimeter, these two up here, are directly in parallel to the resistor, and I'm using the negative terminal as a common point, and I'm using the current measurement port to close the circuit. So there's actually current going through the circuit, through the multimeter and coming out, and simultaneously looking at the voltage across it. Now I have the multimeter set to measure voltage, and you can clearly see, very straightforward, it's telling me the voltage is 4.0159, and if you wait long enough, the last digit will drop because the battery is discharging. There it is, it just dropped by 1 millivolt. Or a tenth of a millivolt. So it seems pretty straightforward. And if I want to measure the current, that's also really easy. I just press shift and DC current, and there it is, and you can see the current is 399 milliamps or so. Again, very straightforward. And this is always live. I can always go back and forth between these two measurements without any issue, because the circuit is closed directly through the relay, through the shunt resistor that is inside the instrument for measuring current. But the instrument also supports dual functionality. Now, the dual functionality can be applied to different combinations of measurements. You can measure DC volt, you can measure AC voltage and frequency, you can measure temperature and voltage and things like that. But that's also very well documented in the manual itself. So you can go and look at what dual functionalities are supported. So I can, in this case, measure DC current and DC voltage at the same time. So I will press dual here and the shift, and it will select the DC current, and a little tiny measurement will show up down here. I'm not sure why they've chosen to make it so small, but it is right there. You can read it. It's telling me the current is 399 milliamps and the voltage is 4.0143. And you can hear the relay. There it is inside the instrument that's clicking back and forth in order to be able to measure the two different functions internally. Now, you may think that, okay, that's great, I'm measuring voltage and current at the same time and everything is good, but there is one little trap that you may not be aware of. Even though you expect the circuit to always be closed, because after all, it is going through the shunt resistor of the multimeter, that's not actually the case. Let me take a multimeter, let me take an oscilloscope, and put it across the two terminals of this resistor here, and we can look at the voltage and see what happens. There we go. All I've done is that I'm looking at the voltage directly across the resistor. Now, one thing I want to also point out is that you don't want to leave this instrument in this mode for very long, because the relays are continuously clicking back and forth, and that's going to age the relays and it's going to give you a long-term problem. So don't leave it in this mode and just forget about it. Only use it whenever you really need to, if you hear the relays clicking back and forth. So all I've added, again, as I was saying, is that I've added the oscilloscope probes to measure the voltage directly across the resistor. Now let's look at the screen of the oscilloscope. I'm going to pick up the camera from here. Bring it up here. Take a look here. Let me turn the slide off. There. You see that? I'm measuring the voltage across the resistor. You would expect the voltage across the resistor to remain constant because the circuit should be always closed. But indeed, it's not. In fact, you can clearly see that we have pulses where the resistor is being disconnected momentarily from, in synchronization with the relays from the load. So in this mode, the instrument is in fact disconnecting and reconnecting the load every time it's switched. And that is not a good thing because depending on the load, that can cause a whole bunch of problems. And if you weren't aware of that, you could actually have an issue. And even damage whatever it is that you're measuring. So, and I could not find a reference to this in the user manual. It wasn't anywhere for me to find. So I'm not sure if this is something that they can get rid of in firmware. I doubt it. Depends on the architecture of how it is internally measuring, and it's done so. But anyhow, something for you to consider. So let's take a look at some diode measurement. Here I'm connecting the output in diode mode, diode measurement mode, directly to my fluke meter. Here you can see that it does put out 6.9 volts, which means that it can deliver quite a large voltage and measure larger junction voltages in different diodes. So here I have a Zener diode, this one, this little one, and of course if I forward bias it regularly, I should get about 0.7 volts, and I do. You can see that it measures 0.7 volts without problems, and if I flip it, now you should be able to measure the Zener voltage, and that is about 1.9 volts. This is a 2 volt Zener diode, so it's pretty close. Depends again on the IV characteristic, depends on where the current measurement is and at what point this guy starts to record the current. But anyhow, this is correct. This is how all multimeters would behave. Some multimeters allow you to identify and actually tell it what current you want to use for the measurement, which would be great, but this one doesn't support that. Maybe it's something they can add in a firmware. Now here I also have a blue LED, which has a much higher turn-on voltage, of course, and you can see that the LED is on, but it doesn't tell me what the voltage is. It's because it doesn't consider this large junction voltage as a functional diode, which is too bad, because if it can deliver 6.9 volts, you should at least be able to measure and show it to us. That should be an easy firmware change, which I hope that they implement, because it would be pretty straightforward to have this ability added. This way you can measure the junction voltage at a 1 milliamp, for example, of current for different diodes. I hope that they add that. And here, for the sake of completeness, let's measure some capacitance. Here I have the unit set to measuring capacitor, and I'm kind of not touching this cable. Of course, as you know, depending on the position of this cable, then the proximity and the proximity to other things, the measurement is going to be completely changing. So I'm going to try not to touch that. So it's now measuring 0.022 nanofarad. I'm going to turn the relative mode on so that it's zeroed out. I'm going to measure a very, very small capacitor of 25 picofarad. Here we go. I'm going to connect this over here and connect this over here and not touch it. There we go. Not bad. It can measure very small capacitors, and it is fairly accurate. I think that's pretty good. We can also go to the other extreme and measure a very large capacitor. Let's go ahead and disconnect that guy and try and measure this very large capacitor. This is 1000 microfarad. Here we go. It's going to take a little bit of time before it gives us a response. There it is, and voila, there you go, 940. Which is also pretty close. I've verified both of these capacitors with an LCR meter, and the unit is very close. So it can handle a large range of capacitor. You can see that the range is at 10,000 microfarads, which is pretty good. It does a pretty good job on capacitors. No complaints there. Now here I'd like to show you the USB software that is supported by the instrument, where you can have a remote connection directly made to the Siglent multimeter, and have a desktop application that connects the multimeter. But for the life of me, I can't get this thing to work. So if I go under connect and click on connect, and I have the USB connection selected here, and I go OK, and it just gives me that, which is gibberish. Of course, it must be because it's in a different language, and it's just trying to display it here in Windows. Now I tried this on 2 different computers. I couldn't get it to work. I'm sure that it works on some other people's computers. Depends on how your hardware is configured and how your drivers are configured. But of course, these error messages are completely useless because you can't tell what is going on. And I think this is still in version 1.0. I hope this is something they update, because it is very useful to be able to quickly have a remote connection for data storage and so on, and collecting data directly from your PC. It's a small problem, but you can see they give you a little interface of the unit itself, and then all the buttons are there, so it should work very nicely, but I just couldn't get it to work to show you what it does. Well, I hope they fix it. And of course there are other functionalities such as the temperature measurement and the math functions, which I haven't gone into too much detail here, but you can go ahead and look that up on the manual and figure it out, and it's fairly straightforward. But I wanted to give you an in-depth look at not just the teardown, but also some of the limitations as well as different functions that this thing is capable of. Like I said, I'm generally very happy with it. I like the big LCD screen. It's really straightforward to use, so it would be a good first multimeter. It has a good user interface, as well as the way they utilize the LCD screen. You can, as you know, if with a bad user interface, it doesn't matter how good the instrument is once you get frustrated with it. It is very slow in my opinion, and that's because because I'm so used to so much faster instruments that I use on a daily basis. But this is sitting in the center of my lab. I use it all the time, so I'm pretty happy with it. For $469 without the GPIB option, it is a very good deal. Now if you want to spend another $500 or $600 and go with Keithley or with the Keysight and their multimeters, that's of course the choice you have to make versus price performance ratio, and of course the brand name if you are particularly picky about that. But other than that, I'm pretty happy with it, and I hope that Siglent sees this and implements some of the bugs that I reported, as well as some of the additional features that I think would be good to add to this unit. As always, if you like this review, please give it a thumbs up, leave a comment, let me know what you think about the review, and if you happen to purchase one of these because you saw it, let them know that you saw my review. I get none of the I get no money from their sales, I get none of the part of the sales or anything like that. It's just for me to keep a good reputation with the manufacturers. Well, I hope you enjoyed it. Until next time.